Hello, my name is Will Johnston, and I'm an aerospace engineering student as well as a research assistant at the Mechanics and Dynamics Lab through the NASA in Kansas Jumpstart program. Today, I will be presenting my research from the past couple of semesters where I worked toward developing new 3D printing techniques. According to a recent Smithers report, the 3D printing market is expected to expand in value from $5.8 billion in 2016 to $55.8 billion within the next 10 years. Such is the case for the most popular and common type of 3D printing called fused deposition modeling, which is the process of stacking melted filament layer by layer to create an object. And one of the reasons why this concept of 3D printing is so popular is that it's relatively inexpensive and pretty simple to use. The workflow to create an object using FDM is this. Users must first create an STL file, then use a slicing software to transform it into G-code, which are the set of instructions telling the printer where to print along the X, Y, and Z axes, as well as how much filament to extrude and how fast to travel. Once the G-code file is created, all the user has to do is send it to the printer and wait excitedly for the finished product. Now, over the years, fused deposition modeling has been fantastic at creating solid structures, such as this airplane replica of the Boeing 787 Dreamliner, or even the Eiffel Tower. But there are so many objects found in nature that 3D printing cannot replicate well at this point, including grass and hair. Seeing this apparent gap in the capabilities of 3D printing, I asked myself, how can fibrous structures be produced using fused deposition modeling? To try and answer this question, I developed a method that relies on the ability of the 3D printer to bridge filament across two surfaces. And it does this quickly so that the filament hardens before it droops down to the print bed. This creates rod-like fibers of uniform thickness throughout their length. I call this the bridging method. And if you wanted to, you can actually just cut off one of the ends and you have fibers that are freestanding and only on one side. However, I was also curious to see if fibers that resemble human hair could be fabricated. So I embarked on an extensive literature review, only to find really only one example from a group of researchers at Carnegie Mellon, in which the G-code was altered to force the printer to extrude a blob of filament and then quickly pull away to create a fiber whose thickness decreases over their length. And if you do this multiple times, you're actually left with a pattern of hair that actually does resemble kind of like a human hair, which is pretty cool. Now, in no time, I was able to replicate this technique, and I call it the extrude and pull method. However, manually editing the G-code for each fiber would take hours and days, so I developed a MATLAB program that will add fibers to basically any G-code file. I even created the program so that the extrusion amount, right here, could be specified, allowing the fiber thickness to be changed. And like I said, this can be added to basically any G-code file. So if we look at the Simplify 3D representation of G-code, and Simplify 3D is just a common slicing software, this MATLAB program would be able to add fibers to basically any object, such as this baby Yoda, or even a Spider-Man, or even if you want to add 4 different regions of fibers to a basketball for some reason, this is how you could do it. Now let's take a look at the results. I was able to print a brush-like object using the bridging method, and I was able to create hair-like fibers using the raised 3D printer that we have in the lab using the extrude and pull method. In this picture, you can see that the change in the extrusion amount can increase the fiber thickness just a little bit. These gray fibers were printed using an extrusion amount of 2 millimeters, whereas these blue ones were about 1 millimeter. And you can see that the gray ones are slightly thicker than the blue ones. And of course, with the ability to create hair-like fibers, I just had to print them onto a troll. And these fibers can even be cut, braided, or curled, just like human hair. And unfortunately, you're not able to feel this, but it really does actually feel like human hair, which is pretty cool. Now, to get a sense of the thickness for these fibers, I performed an analysis using the microscope that we have in the lab. In general, the bridging method allows the fibers to be uniform throughout their length, while the extrude and pull method produces fibers that are thicker at the roots and kind of thinner toward the middle. Again, kind of resembling a human hair type of thing. Of course, these fibers would make for great knick-knack gifts, such as this troll right here, but I wanted to expand their applications beyond just those knick-knack gifts. Fibers in general have been known to be effective sound absorbers, so I created 37 different cylindrical samples, like this one, of varying fiber density and thickness, and tested them using the impedance tube that we have in the lab. Basically, the sound waves are moving through this impedance tube until it hits a sample, and the microphones here detect how much sound is absorbed after it hits a sample. I hypothesized that spacing the fibers closer together and making them thicker would cause them to absorb more sound. And what I found was that these fibers are actually effective sound absorbers at low frequencies, especially between 2000 and 4000 hertz. It actually reaches a sound absorption coefficient close to about 0.85 for the most fiber dense sample. And currently, I'm working on with some other students in the lab to add 3D printed fibers to triply periodic minimal surfaces, such as this gyroid right here. It's just a type of fancy geometry that is also known to be somewhat decent at absorbing sound. And you can see that this results in a sound absorption coefficient that reaches nearly 1 when these fibers are added to these gyroids, especially at a frequency between about 1500 and 2500 hertz. And this indicates very effective sound absorption qualities. In general, my hypothesis was correct in the sense that increasing the fiber density and the thickness are the best two ways to optimize the sound absorption characteristics. Now, throughout all this research, I couldn't help but notice how exciting 3D printing can be, but I also realized that it can be also quite expensive. Between the printer itself, the filament refills, and even maintenance on the printer, entering the realm of 3D printing can cost $500 to thousands of dollars, according to the website All3DP. Considering the 3D printer is a perfect device for STEM education, I began to ask myself, how can I make 3D printing more accessible to almost everyone, and particularly school-age children who otherwise would not have access to such a wonderful tool? I figured that although schools and K-12 students might not have access to a 3D printer, they certainly have access to mobile devices. Therefore, I created an iOS application that acts as a virtual 3D printer interface to teach users about the role of G-code in 3D printing. Users can manipulate any of the X, Y, or Z axes as well as the extrusion amount to create the object, and then view the line of G-code at any time right here. The app also has a print playback feature on the right here, so the user can see the nozzle moving around as it prints their object, almost as if it was a real 3D printer. And this app also allows the user to see all the lines of G-code that they created all at once as well. Of course, the most exciting part about 3D printing, which is actually being able to physically hold the object that you created, can only exist with a real 3D printer. With that in mind, I tried to make it so you almost have that same experience within this app. So I added an augmented reality feature so that users can see their object placed directly into the world through their device's camera. So in a world where everything seems to be virtual these days, including this presentation, I sought a way to make 3D printing virtual so that it can be more accessible to just about everyone. In conclusion, my research over the past couple of semesters has developed two novel 3D printing methods to fabricate fiber structures, including a MATLAB program that allows users to easily add fibers to any object in a way that was not previously possible. In addition, I explored the sound absorption characteristics of these fibers and found that they can be effective sound absorbers, especially at low frequencies. Finally, I developed a virtual 3D printing app to make the process accessible to just about everyone. For the future, I expect to continue to look at more ways I can expand the quality of 3D printing and introduce new, more novel printing techniques. For instance, in the past few weeks, I was able to modify a desktop 3D printer to print with a syringe. And just yesterday, I was able to print using grape jelly using this syringe, which is pretty cool. Now, this can make 3D printing delicious in addition to making it even more fun. For example, last night, I actually added this WSU kind of block lettering onto the piece of bread here. And of course, I had to eat it after I was done. As far as the app goes, I plan to submit it to the Apple App Store in the coming weeks, and I plan to create a virtual workshop this summer with our lab at WSU, hopefully, to get K-12 students interested in 3D printing, as well as one day hopefully having a career in STEM. Finally, I'd like to greatly thank my faculty mentor, Dr. Sharma. After a year and a half ago, I knew nothing basically about the research process or about 3D printing, and he has helped me been a guide for me through all of it. Last week, actually, we found out that our paper dealing specifically on the sound absorption of 3D printed fibers was accepted into the journal Additive Manufacturing, which was pretty exciting. I'd also like to thank the NASA and Kansas Jumpstart Program, as well as the Undergraduate Research and Creative Activities Grant Program and the Acoustical Society of America. Thank you very much for watching my presentation.